Hello, hello. Am I audible?
Yes.
Thank you. Hi, everyone. I'm Yash, and today I'll be taking a lecture on DP. Uh, is anyone else joining, or should I start? I will start. Okay. So, let's start with the basics of DP. So, DP is dynamic programming. So, what is actually DP? So, when you have a problem and you break it into sub problems, or you break it into smaller problems, you solve those problems and then you use those smaller problems to solve the bigger problem. So like, for let's start with an example of a Fibonacci sequence, which has a recurrence of f of I is nothing but f of I minus 1 plus f of I minus 2, and f of 0 is 1, f of 1 is 1. So in this sequence, what you see is that you can find f of I is what, if suppose you want f of n, then you can find f of n using the values of f of I n minus 1 and f of n minus 2. So the ith element is the sum of the previous two elements of the Fibonacci sequence. So if you like, just think of a recursive approach, like a very basic, just read the problem and how will you code. uh, so if you just think of it as a recursive thing, then you can just actually write this recursion where you have like, and you just put uh, return. So you can just, this is the simple Fibonacci sequence, and just add a base case as well. Uh, oh, f of 0 is 1 and f of 0 is 0 and f of 1 is 1. So if, oh, 1 return I. Oh, yeah. So this is the very basic recursive code. Oh, okay. Ignore the way it's written, but yeah. So but if you see, then you will see that suppose you want f of phi, then f of phi is nothing but f of 4 plus f of 3, and f of 4 is nothing but f of 3 plus f of 2. So you'll see that f of 3 is actually called twice. F of 3 is nothing but f of 2 plus f of 1. So f of 2 is also called a lot of times. And as the n increases, this value, like number of times the smaller f's are called, are increased exponentially. So if you want to find f of n, then this recursion gives the time complexity of exponentially large, around 2 to the power n, which is like really bad, right? But what you can observe is that you are calling the same f of I multiple times, but the value of f of I is constant. It's going to be remain the same, right? So what if you just store that value? So basically, you are solving for f of I, and you are storing that value, and you are using that f of I to solve f of I plus 1 and f of I plus 2. So basically, for some n, you are using n minus 1 and n minus 2 values which you have calculated to find the current value. So this is nothing but, this is the basics or the crux of dynamic programming, where you solve the bigger problem to too small, like too many sub problems, smaller problems, solve those smaller problems using more smaller problems, and eventually you just combine them using the help, and they merge and finally solve the new problem. So uh, this code itself is like can be like optimized using memoization, which is nothing but the top down approach. And using that, the time complexity can be significantly reduced. So just if we just add a line, if f of I not equals to -1, return f of I, and just add f of I equals to. So here we are just storing f of i's value, so that in case if f of I is 1, that means that it has not been calculated yet. Then we just calculate it. Oh, sorry, f of I is not equals to -1 means that it has already been calculated and its value we know. So we'll just add it. We'll just return that value, and else we'll just calculate it, store it, and return the values. So this is the top-down approach. Uh, yeah, in recursive approaches, you can go from 0 to n or n to 0, whichever is comfortable, and I'll come to that. But in this current case, we are going from n to 0. So for solving the nth problem, we are using the previous problems to solve smaller problems, and then using that, we'll be solving the nth problem. But sometimes you can also go like in this case itself, if you just put this case is tough, but in other problems you will see that you also sometimes go from 0 to n. Yeah, so this is the recursive memoization approach. But the same problem you can also solve using iterative method. So what you do is you will actually, for each possible sub problem, you will find the value for that sub problem, and then you will go ahead and eventually you will find the value of the problem you have. So you can just use a for loop. You can just have the base cases same, like f of 0 is 0, f of 1 is 1, and then and then nothing but f of I is simple. This is the iterative method, and both should be fine. Iterative is faster than recursive. Yeah, it's a bit faster, but depends. Sometimes in iterative method, the problem is that you need to find each and every possible outcome, while in recursive you only, so the only difference you can see between iterative and recursive is that here we are checking that if it's not if it's calculated, just return, else we'll calculate this. So we are only going to states which are like needed to solve the nth problem, like for the problem we have, right? But in iterative, you will see that suppose this was f of I minus 1 and I minus 3, right? So you will see that for n, you actually don't need f of I minus 2 at all, or just remove this. Oh, right now it's needed. But if it's this, then you actually don't need f of I minus 1 and f of I minus 2. Still, you will calculate in the iterative approach, while in the recursive approach, you won't calculate that. So, generally, it's iterative approach that is more faster, but it doesn't matter. If iterative passes, then recursion should pass for that problem, and you should just continue with what you are more comfortable with. If you can think in recursion, then just do recursion, and it's easy to convert between recursion and iterative generally if it's not a difficult problem. Yeah. Where did convex cell come from? Okay. Sure. Right now we are going from the basics. Convex cell is a bit advanced, so I think you won't need convex hull in ZCO to qualify. Yeah, so during the INY time, we can keep it. Yeah, the time complexity for this Fibonacci is order of n. Iterative is used to find many quiz. I don't understand what you mean. Yeah, recursion is a stack, so it's like the time complexity matters. Generally, the constant don't matter, so it doesn't matter if it's iterative or recursion. Most of the times, it's like a very rare case. Yeah, I think you should be like you can generally work on whichever is more comfortable to you, recursive or iterative, but you should be familiar with recursion because recursion is like needed in a lot of topics, and generally some things you can solve using recursion, you can't solve using iterative, or it's like very difficult to convert it into iterative, but it shouldn't be a problem. Yeah, recursive. I also find recursive easier. Okay, so let's move on to solving the problems. But the main idea of DP is that first you define a subproblem, then you need to find what relation is it, like the recurrence formula or the relation, and of course you need to set that base case and then just decide how we are going to loop and what's the order in which we are going to loop. So let's start, and it's very important that you understand which uh, hello, am I audible? Hello. Okay, so it's very important that you understand which problem is or is possible to solve using DP and which is not. And yeah, it's the best way to learn something is best for practicing it. So I'll be solving the some of the classical DP questions with you, and it's really important that you understand how to think and how to approach. Yeah, I'll explain the recurrence in fact. So that's why it's the lecture is so that you understand that how to think when you approach a problem, and how do you find the solution for a DP. So let's start with the easier one, the frog jump. So the frog jump is basically you are given n stones, or just say that let me it's okay, I will not delete it. So let's say you have n elements. Okay, and the frog can jump from ith element to I plus 1 or I plus 2. So these are the two possible options, and uh, the cost of jumping or the energy to jump or whatever it is. Suppose this is AI, this is AJ, this is AK. Oh, it's basically AI plus 1, not AJ. And AI plus 2. Right, so only these two possible is there, and this is the ith element. So let's suppose you have some elements ahead as well, and now when you jump uh, from I to I plus 1, the cost is absolute value of AI plus 1 minus AI, and when you jump from I to I plus 2, the value is the cost is nothing but ai plus 2 minus ai absolute value. uh, yeah, so these are the costs, right? So when you see this problem, probably you might think that we just jump to the lower cost value, and you can go on, you need to minimize the cost, so you can just go on to lower cost and continue. But that's not the case, because sometimes you have like an element x, you have x, and suppose this is like a value greater and the next one is value lesser. If you go here and these both are like a low values, then after this you have a lot of cost to go down again. But if you go down and then these values are more less, then you can easily go down with lesser cost. So you see that the greedy solution does not work. So when you find such minimization problems, sometimes it's greedy, sometimes it's binary search, sometimes it's dynamic programming, sometimes it's something else. The main thing is you need to understand what the problem is. You need to observe certain things, and then you need to think. Like this is where it's very natural to think greedy in this, but it's not going to work. So you need to observe that what's actually happening. So now let's think of how to solve this. So what we will do is, since we can't use greedy, we need to actually check all possible options. But of course all possible options would lead to time limit exceed, right? Because it's like, again, exponential power. So again we will use the same thing. We'll see that for some I, if the frog is at I position, there are only two options, right? Oh. Why is it? Yeah, there are only two options. So you don't care how you came till I, and you need to reach n for all things. So if you are at I, you just only care that I can go at I plus 1 and I can go at I plus 2, and then I reach n from there. I don't care how I go. So this is basically, you are just making it a smaller problem using abstraction. Okay, it's hard to understand, explain abstraction, but basically you're just ignoring everything, all the unnecessary info. You are just looking at the necessary info, and you can see that this is just order of one of checking which one should I go if I know the answer from this part to n and this part to n, right? And if you see, then it's almost similar to, like, it's kind of similar to Fibonacci sequence. So you can see that for some a of I, if you just think reverse, then for some a of I, for some a of I, you just come from a of I minus 1. Like the only possible way to reach is a of I minus 1 or a of I minus 2, right? So if you have answer of a of I minus 1, which is the minimum time, energy, or whatever to reach a of I minus 1, and if you have answer for a of I minus 2, then you can find the answer of a of I minus a of I using these two things. So this builds a relation where dp of I is nothing but minimum of dp of I minus 1 plus this element. So where's, yeah, so dp is hard to write. I minus 1 plus absolute of a of I minus 1, and this was a of I minus 2 dp I minus 2 plus, and it's nothing but the minimum of these two. So and dp is basically the minimum time, cost, or energy, whatever you need to reach ith stone or ith position. And dp of, so to reach, yeah, this is equal to dp of I. So minimum time to reach the ith stone is nothing but minimum time to reach the I minus 1 stone and going from I minus 1 to the ith stone, or minimum time to reach I minus 2 stone and from I minus 2 stone going to I stone. So this is the recurrence for the frog jump problem. And you can take the base cases where dp of 0 is 0 and dp of 1 is nothing but reaching from dp of 0. So just calculate that answer, and then from 2 onwards you can use this relation. And this you can code both iteratively or recursively. Recursively, uh, if you think uh, iteratively, it's already there on the SPY block. So I'm not going to explain the iterative, but here what you can do recursively is you can also go from 0 to n. So it's not necessary to follow this relation. Just in recur, so the easiest way to think recursion is just copy what the problem says. So if you have suppose recursion, I'm not writing all the variables and stuff, but then you have base case. You just write the base case and just say answer of I is just you can just return dp of I is recursion I plus 1 plus cos 2 I plus 1 plus recursion recursion I plus 2 plus cos 2 I plus 2, and this is nothing but min. So this is exactly what the problem says. You can jump from I to I plus 1 or I to I plus 2, and the cost is this. So it's exactly what the question says. I've just written it. I'm just storing it in a DP array, which is like instead of if you just do recursion, it's if you just remove it, it's exponential time. If you just memorize it with the DP, so you avoid recalculating, and it's order of n. That's it. So generally, if you understand this, then it's easier to think recursion as well. And if you understand the recurrence part, then technically you can write both recursion and iterative. Okay, a lot of messages. uh, I think there will be more DP lectures. I don't know exactly who's going to take, or uh, that should be contacted to the SPY founders. This isn't greedy because what greedy will be is you have three stones, right? This is I minus 1, I minus 2. So greedy is when you see the cost of I to I minus 1 and I to I minus 2, and whichever is less, you go with that thing. But you are not going with that thing. You're actually taking both options. You're considering both options. And you are finding what's the best answer if I go to this option and if I go to this option. Right? Which actually my DP stores. DP of for this DP of I minus 2 and I minus 1. So if you remove the DP I minus 2 and DP I minus 1, then it's a greedy and it will fail, as I initially explained. But you are technically seeing all options, finding the answer of all options, and then finding the minimum. That's why it's not greedy. Yeah, Avigna said it right. Is there anything else? There's a lot of messages. I think just I can go back so much. What are the base cases here? Base cases is dp of 0 is nothing but 0 because you need 0 energy to go on. You are starting on 0, so you dp of 0 is 0, and dp of 1 is dp of the cost of going from 0 to 1. So it's like a of 1 minus a of 0 absolute value is nothing but dp of 1, and dp of 2 from dp of 2 onwards it follows the recurrence. Yeah, it's possible to show the code if it doesn't take. Okay. Uh, is my screen visible? I don't know. Okay. So which problem is it? Yeah, frog jump. Yeah. So if it's just for one element, then its answer is zero. If it's dp and dp of 0 is 0, dp of 1 is absolute difference of h1 minus h0. These two are the base cases, and from 2 to n, dp of I is nothing but dp of I minus 1 plus the absolute value, like the cost of going from I to I minus 1, and dp of minimum of dp of I minus 2 and cost of going from I to I minus 2, and just print the final value to reach n. Mm. No, convex hull will not be discussed. It's a too much for the first lecture of TP. I'll be discussing two past ZCO problems, and one of them is around 1900 or something. So, but that will be discussed at the end. Yeah, I think there will be advanced lectures. Okay, just ask like about lectures to the admins. Why it works? So, okay, so just think of the solution. Just think that where's the, yeah. So, oh, oh, oh. Is my annotation visible? I hope it should be. Yeah, okay. So, what you are doing is you are actually calculating all possible options. Uh, so, if you just see the recursive basic code, right, which I wrote, then it's nothing but dp of I, it's nothing but answer equals to absolute of value of I to I plus 1 plus recursion I plus 1, or absolute value of I to I plus 2 plus recursion of I plus 2. So this is actually what the prompt itself states, that if you are at the I position, you can go to I plus 1 position with this cost, and then recursion of I plus 1 is just reaching to n. If I equals to n, return 0. So if you had reached the n position, you just return 0, or it's n minus 1, whatever. But you understand the logic, that you are actually checking all possible options, because what the problem states, from I you can go to I plus 1, and then whatever you go from I plus 1 to the two options, and this is I to I plus 2 and all possible options. This is actually, I think, around 2 to the power n time complexity, because like it's 2 into 2 into 2 into 2 into 2. So this is start AI companion. No, please don't disturb by doing this stuff. So basically, this recursion is the brute force of the problem, which is to the power n, and the only thing you are just doing is storing this answer in the value of dp. Oh, oh, oh. Why can't I edit? Uh, oh, just yeah. So you're just changing this with dp. Uh, this value becomes dp of I. So if this value becomes dp of I, because this value is going to be constant for I, right? It's not going to change. So if you just store this, then this to the power n solution, the brute force solution, becomes a dynamic programming order of n solution, because each I will be calculated at most 1, and each I is calculated in order of 1, right? I hope that answers the question. Is the final recurrence this? It can be written either ways. I plus 1 to I plus 2 is nothing but just copying what the question states and writing it. If you just put I, if you, this is like going from 0 to n, and if you go from n to 0, it's like I is I minus 1 plus I minus 2. Generally, you can go straight in recursion. No, actually, you can go straight in both. It's like how you loop. It doesn't matter really. Sometimes it matters, but in this, it does not matter. You can change the recurrence accordingly. Yeah. So I'll share the whiteboard again. Uh, um, yeah. Oh, I should use existing whiteboard. No mind. So, oh, guys, don't do that. Oh, oh, oh. I just closed it by mistakenly. Just- Yeah, so till then, you can think of the next problem. Next problem I'll be doing is, let's go on the coin change problem. Yeah, yeah, we can do the coin change problem. Or let me see what problems are there. Oh, we'll do this one. This is nice. The grid one. Grid path problem. So grid path is basically you are given n into m grid, and yeah, thank you for sharing it. So in grid path, you are given n into m grid, and either grid cell is empty or it's blocked. If it's empty, then you can pass through that cell. If it's blocked, then you cannot pass through that cell. And so you have some grid of n into m. Yeah, I'll be recommending problems soon. I need to go through the problems myself, but this is some grid where these are empty cells, these are block cells, this is a block cell. I'll send the possible like advanced problems, good quality ones on the server itself after the lecture. So suppose this is like a grid. Okay, so this is like a 3 by 4 by 3 grid, and you are initially at this position 1 comma 1. You need to reach this position 4 comma 3, right? Reach this position. This is 1 2 3 4, and subsequently you just assume that. So now you need to find the number of ways you can reach from 1 comma 1 to 4 comma 3. This is the problem, and I'll give you like 30 seconds to comprehend, and then I will go on to the recurrence. Yeah. uh, so so no, the number of, okay, the number of ways in this one is 1. But let's make it this, and this. So the number of ways to reach from 1 to 1 and n to n is, um, you go from oh, you go this one possible path and two possible path, right? So just see this problem. Probably you might think there might be some NCR or whatever it can be. It can be a counting problem, but what you see is, you start this problem. You see, you just start by thinking, what do I observe in this problem? The first observation, if it's block cell, that is a 0. You can't go to the block cell, and you can't use this block cell to go somewhere else. So this answer over here becomes 0, which is why it's not a maths problem and it's a DP problem. Though I don't know if it can be solved using maths, but yeah. So you see that this won't contribute, and this also won't be possible to reach. The second observation is that to reach cell I, comma j, you can either go from, like, come from up or come from left. So these are the only two possible options, right, to come from. So suppose you can reach this element or reach this cell, and you can reach this cell in some ways. Suppose it's x ways and suppose it's y ways. Then for the I comma j, it's just summing these two ways, right? Because those are the two possible options to reach. So you just basically solve the problem using some sub problem in the thinking process itself. You're just thinking what's the answer for this and number of ways from this to this, and of course these ways won't be repeated, because if I'm at some position, if I'm at some position, and if I came to this position and then I came to this position, so once I come to this position, I can never go to this position, and if I come to this position, I can never go to this position, right? So it's never possible that I come this position and go. So no ways are repeated, right? So once you find that there's no repetition, you can, the number of ways for this cell is nothing but adding the number of ways for this cell and adding the number of ways for this cell. So you just solve the problem using two sub problems, but again you need to solve this sub problem as well, right? Similarly, you need to solve all smaller sub problems, and eventually you will reach as a base case where 0 comma 0 and number of ways to reach the first cell is 1 if it's a empty cell. Yeah, and the only crux is that number of ways to reach a blocked cell is 0. That's the only case. So this all basically developed a recurrence formula itself, that to visit some node dp of I comma j, or yeah, you can name it dp, is nothing but dp of I minus 1 comma j plus dp of I comma j minus 1. Yeah. How can we count the number of ways we reach place? I don't understand that. Where does what an I and j denote? I denotes the ith column and j denotes I denotes the ith row and j denotes the jth column. So if you want to reach at cell I in the ith column and the ith row and the jth column, then how many ways can you reach that cell? It's either you come from up or come from left. So left is dp of I minus 1 j possible ways, and up is dp of I comma j minus 1. If it's a block cell, then that dp will be 0, so it's automatically not adding to your answer. How do we count the number of ways we can reach a place? It's how we are doing it by dp, right? So this is okay, this is basically a recurrence, and the base case is that dp of if it's a 0 based index, then dp of 0 comma 0 equals to 1. If array of 0 comma 0 not equals to hash. So if it's not a block cell, then dp of 0 comma 0 is 1, else it's 0, right? Else dp of 0 comma 0. Yeah, hash equals to 0 because you can't visit that cell, right? So how many ways can you visit a hashed cell? It's 0 because you can't actually go to that cell, right? That's why it's 0, and it can never contribute, right? Because if you can't reach that cell, you can't go through that cell, then the contribution is also 0. And here contribution is equal to the number of ways you can visit that place, which is 0. That's why it's the like a special case. uh yeah, that's why the first observation was about the hash thing. So it's how you approach the problem. You just look at small observations. Even the harder problems you start, or you just see, you need to look at the small observations, and then you need to build that observations or use that observation to build a bigger observation and find the crux of the problem. So we just used small observations to make this recurrence formula, and we basically solved the problem. uh, So we create base cases for deeper and then iterate through the values ij and use recurrence formula. Yeah, in the recurrence also you need to use the case. If array ij equals to hash, dp of ij equals to 0, else. Yeah, so this is the recurrence if you want the complete recurrence. And yeah, if the last cell which you want to visit, n comma m, is blocked, then you can never reach that cell, and automatically from this recurrence it will just assign it to 0, right? Because it's blocked. So you can just think of some random corner cases and you need to include them, or you just think that it's working, then wow, good job. Yeah. Do you all want to see the code? Then I'll share my screen. Yeah, is it possible if I copy it here? Let me see. Yeah, okay, I can copy it. So this is the code, and you're just taking this as the input. It's not really my code, so just I have to deal with it. But and this is the dp, and this is the base case. So if it's like no hash is there, it's an open cell, then it's 1 because you started at 0 and 0, right? It's one way to reach 0, which is the starting point. And else it's 0, which is assigned over here. So all dp is assigned 0. Yeah, and then you just loop through the grid. You need to loop like if this is the grid. Yeah, if this is the grid, so I is increasing like this and j is increasing like this, then either you go like this, like row y, each row you go from 0th row to nth row, and for each row you go increasing column, or you go increasing column, like for each column you go increasing row. Either way, but generally it's like for each row you go increasing column, but it depends. And that is important because for dp of I comma j, you go either to the previous row or the previous column. So both the previous row and the previous column should be already solved to solve that dp of ij, right? And so here we go, for each row you go increasing column, and if it's a block cell then it's 0 because it's already assigned 0, initialized with 0, so you do nothing. If it's if it's in the grid, this is also important. If I is 0, greater than 0, because if it's not in the grid then it's not possible, and if j is 0 then it's just Uh, where's the code? Oh, is the code visible now? Or you can't still see it? Follow them. Is prefix sum equals to dp? I don't know. It's a debate. Technically everything is dp, and technically everything is not dp. Mm, you can say prefix sum is a dp. Yeah, it's kind of dp. It follows everything: base case, recurrence, and but okay, it has a different name. So yeah, do you all have any doubt on this problem? No. Okay. Then the next problem I'll be doing is knapsack. Uh, there are two problems of knapsack. I won't be going through both. I will be going through one, and the other is for you all to practice. Links. Yeah, we're gonna please share. I have it. I've sent it in the announcements. Uh, uh, and yeah, and I'll also explain the problem statement, but sure. So let's go on to the 01 knapsack, which is the original or the more classical one, I would say, where uh, uh, delete all this. Yeah. So this is the problem where you are given like n items, and each item has a weight. So these are the items. It has a weight w, I. Not everyone has different weight. Right? Suppose you have like a pizza, pasta, pencil box, right? So each item has a different weight, and each has a value vi. So let's say pizza's cost is vi, pasta is like cheaper, so vi v2, sorry, or v1, right? And pencil box is like very cheap, right? And you have a bag, and you can put some things in the bag, but of course you can't put, or probably you can't put, not of course, sometimes you can't put all of these. And what you might decide that okay, pencil box has a better value, it's more important to me than pasta, so I will put pencil box and pizza or something like that. So basically you have some elements or some items that have weight and value. You have a bag where you put those elements, but the bag can only carry weight w, it can't carry more weight. There's no issue of volume, and of course for each of the element you have value. Or you can sell pencil box at an expensive cost, then you would just take that and have a greater advantage, right? So your goal is to maximize the values while keeping the total sum of weights at most w, right? So why does it say following post? So, yeah, so this is the problem, and the constraints are n is still 100 and w is still 10 to the power 5. And the second version is where w is 10 to the power 9, and which you can solve quite easily after you understand the first one. It's kind of test. If you understand the first one, then you should be able to solve it on your own. Else it's on the SPI block, so you will have the edit over here. Yeah, it can carry less than weight w. Weight w is the max limit. Else the bag will like tear apart. We can use greedy. Yeah, again. See, that's the thing. If you see the problem, you should think all perspectives. Because when you are solving somewhere, you don't know if it's DP, then how you solve. So you think of everything. So it's a good thought that is it a greedy or can I solve it using greedy? So suppose I have some values in ascending order, right? Oh, how can you all edit? Okay, yeah, I disabled it. So basically v3 is greater than equal to v2 is greater than equal to v1, right? Yeah, I'll also give numeric examples, don't worry. And you have weight w1, so w3, there's a big weight w3 w2, yeah, w2 w1, right? So what will be my greedy? One of my possible greedy is I look at the values, right? So if I look at the values, I will of course take v3 first, then I will take v2, then I will take v1, right? So this is my preference. But what if my weight is 5, v3 is like 10, this is 9, this is 8. So the values hardly change. But according to my greedy, I will go with 10, right? And my weight is, this is 5, this is 1, this is 1. So I can actually take two ones and have a sum 17. But if I take this 5, I cannot have that sum. And the second greedy might be you just greedily take the weights, right? If it's 1, 1, and suppose this is 5. But what if for the weights, this is like 3 and this is like 4? Then if you take 1 and 1, then you can't take this 5 in the bag, of course. But your sum is just 7. Instead, you just take this 5 and your sum is 10, right? So here you see that greedy is not possible because there are two things, right? And these two things don't have a correlation with each other. So it's very difficult to find the answer using greedy if they don't have any correlation. You can't observe or you can't deduce anything in the greedy. You can't think of something. Then what you will do is let's do brute force and optimize it, which is basically dynamic programming. So you just understand that okay, we need to check all possible options. There's no observation or there's no breakthrough in it. Then I need to go dynamic programming because that's actually trying all possible options in an optimized manner. So let's think how we'll solve it. I'll give you like 30 seconds to think. Yeah, so what if now first thing, if you want to go brute force, you need to understand that there are two variables in this case. One is the weight w and one is the number of item, so which item you are, right? Because each item has a different weight w and another variable is weight value I. So and you need to maximize this, right? So when you need to maximize this, when you are on the ith item, so suppose you have first I items, okay, the ith item has a weight wi, right? And if you can take this item or you cannot take this item, right? And if you take this item, you get vi value. If you don't take this item, you don't get the vi value. When can you take this item? When your total weight w remaining in the bag, it's not the total weight, it's like the weight remaining in the bag is greater than equal to wi, right? So suppose you are at the ith item, you have first I items, and you have total weight W. Then what is the best possible answer? The best possible answer is either take this or not take this. That's the all possible options. If you take, you can only take this when this condition is satisfied, and if you take this, then you get the answer Vi. And then what's the new problem? The new problem is when you have I minus 1 elements, because we assume that we have the first I item, so now we have I minus I item because we already used the ith item. When you have I minus 1 elements, so basically you are at the I minus 1 position, you have Wi minus 1 as the weight of the I minus 1th position, and value is Vi minus 1. This is the sub problem, right? And you need to maximize your value when you have weight Wx, right? And this is the smaller problem, and plus Vi, if you take Vi, is the answer for us. Now let's make this a little better recurrence. So now I can identify that if this is my recurrence, I am maximizing Vi. So Vi will be the thing that will be stored in the DP. So some DP of ijk whatever will give me a value Vi which is maximum value, right? And because here I want the maximum value of Vi in the bag plus this Vi, right? So I am maximizing Vi, and for taking Wi, I need the current weight that I have in the bag, right? So to check if it can be taken or not, I need the current possible weight that can be added in the bag. So this gives me a variable of dp. So let's say dp, here we know that dp should have one of the positions as w, right, which is the remaining weight. And the second thing is the index at which we are, to understand what is the Vi value and what is the Wi value. So it's nothing but dp of I comma w. It's a 2D dp because there are two variables, right? And now if you want to find the recurrence, let's make a clear recurrence. dp of I comma j, where I is the I equals to index, j equals to weight that can be added in the bag, like the maximum possible weight, and dp of ij is nothing but dp of ij is dp of I minus 1j. Suppose you don't take this item in the bag, you are saying like pizza, who eats pizza, damn. So you just ignore that thing, then of course you won't get the value that pizza gives, right? So it's just the remaining I minus 1 items, and you still have that weight j in the bag. This is the one option, right? And you need to maximize weight. So of course, maximize the value, sorry. So you need to maximize dp of I minus 1 comma j, or you take pizza, then you have like a value val of I, because at the I position, plus dp of I minus 1 and j minus w of I, right? Because you have now weight less, the weight is decreased by wi because you take pizza, so you can't take much. And the only thing here we are missing is the thing we observed, that on this second case is only possible if wi is less than equals to j, right? Because if pizza's weight is less than the maximum possible weight that can be taken, then only we can add this, else we it's like 0. Not here. Yeah, this is the recurrence formula for 0-1 knapsack, and the time complexity would be n into w, which is 10 to the power 7. So it's fine. If you want to optimize it a bit, you can optimize the space, because you just see that for ith index, you only go to the I minus 1th index, right? So you can reuse the space. You just remove the state, but you loop through I twice. So the time complexity remains the same, but 10 to the power 7 might be too big for us for memory limit. It's not big for time limit. So you can just remove this first like uh, variable and just loop, and you know that you just keep store 5 minus 1. So that optimization generally are helpful in harder problems where they want to like bring a differentiation. And yeah, but do you all have any doubts? You can think of the other problem. The other problem is the second knapsack one is you have n is still 100, weight is 10 to the power 9, and the values the values in the other knapsack problem are just 10 to the power 3, right? So if you have any doubts for that, then you can. If you understand this, then you can understand this version as well. Just think how to solve. It's not this, but some way. It's nice, and it's there on the SPR blog for discussion. And if you have any doubt, you can ask me right now itself. So we should add 1 at last for the recurrence, as we making the recurrence by first term. Should add 1 at last. Yeah, I will go show the code. So, I don't understand. What do you mean by add 1 at last? If it's about the index, and I'm not going so deep into that, I'm going more into the logic and the recurrence. And these nitty-gritties like corner cases and stuff should be done like when you're about to code. Right? I will share the screen for the solution. Is my screen visible? I think it is. Yeah. So this is the recurrence. This is the recurrence, right? And is eraser. Yeah. So this is the code, 2D DP solution. So this is the weight array and the value array. Oh, you meant this -1. Okay, yeah, this -1 should be there. So you just take the weight array. This is the DP, and you have W plus 1 because weight can be 0 to W, right? And initially you initialize with 0. So when you have 0 items remaining, for any weight you have possible value 0, which is like initialized. And here it's 1 based, and here it's 0 based. So this is the conversion from 1 base to 0 base, which is, if you are at I, then it represents in the 0 base you need to subtract 1, right? And you go from for each item. If you have the I items, then you go for each weight, and if you have W weight remaining, and is the W weight like can we take the current element, then we take the max of things, else we just go on to the previous element. Oh. Yeah, let's look at some doubts. Where is the blog? I have sent the link in the announcements. Yeah. In the blog only the one of the ZCO problem solutions is not added, which I will be going through and I will be adding after the lecture. But all other things, even some problems not taking like explained in this lecture, are there, which I had planned, but that was if time permits. Yeah. Oh, yeah. So that is for this. Now, if you have any doubts in any of the DPs, any of the knapsacks, then let me know. Else, we'll go on to the next ZCO past ZCO problem. Um, yeah. So the problem statement. Where is it? Where is it? Where is it? Yeah. So the problem name is equal gifts, I guess. Yeah, it's a past ZCO problem. Equal gifts. And the problem basically just tells that, oh, it's a long problem. So basically there are n pairs of books. Each pair has two books with some cost. Okay. And the goal is to divide the books so that each pair is split, one book to Lavanya and one book to Nikhil, and the difference in total value between them is minimized. So there are n pairs of books, right? And it's very important to read books, study hard, and each this book and this book is either like goes to L and N, right? So either this goes to L and this goes to N, or this goes to L and this goes to N. So there are two possible options, right? Uh, yeah. So I'll give you like 1 minute to think, understand the problem, think of the recurrence, or think anything you see by seeing this problem. Yeah, we calculate the difference. Yeah, good observation. Actually, we do. So if you all understood the problem, then I might not just explain this thing like the example. If you don't understand, then let me know. I will explain the example. Okay, I assume that the problem is clear. The first pair is given randomly, then we give the smaller to the smaller one. I don't understand. What do you mean by given randomly? We give the smaller one to the smaller one. What do you mean by we give the smaller one to the smaller one? 3 5 here, 2 is given to 3. So 3 comma 5. Where did 2 come from in 3 comma 5? Never mind, continue. Okay, thank you. So basically you have given n pairs, and each pair can either be given to Lavanya or Nikhil, and you need to minimize the sum of the books that they both have. Absolute, of course. Right, so the first observation is that since at least for some ith pair, one of the books will go to one of them, right? So at the end, what do you get? Like, if you're just thinking, you just think that it doesn't matter. Like, if the books have value 3 comma 5, isn't this equivalent to books having value 0 comma 2? Because if I give 3 to Lavanya and 5 to Nikhil, then the absolute difference actually subtracts this, right? So it's either minus 2 absolute value, which is 2, or 3 minus 5, which is 2, which is equal to 0 comma 2, right? Which is equal to the difference, right? That's why at them they are getting subtracted, and one of them will go to one of them. That's why we will take the difference, right? So this array of pairs can be converted into an array of their differences, and this difference can be absolute value because at the end it's an absolute, right? So if I am thinking of giving 3 to Lavanya or 5 to Nikhil, or 5 to Lavanya or 3 to Nikhil, at the end the difference is 2, which is getting increased to Lavanya or to Nikhil, right? So we can just think of that as a positive value, which either we will assign to Lavanya or we will assign to Nikhil, right? So this is an array of positive values, and each value we need to either assign to Lavanya or to Nikhil, and we need to minimize the difference between the sum they have gotten assigned. Yes, Tiffin doesn't change. I see we can transform the problem into knapsack. No, we aren't transforming the problem into a knapsack because how can you transfer into knapsack, right? You can probably. Yeah, each book has a weight, but it would be different from knapsack because what you are doing is, yeah, I will explain what's the difference, but it's quite similar to knapsack. You can convert it. No, so we don't have anything called value here, right? So we don't care of the value, but what we need is some weight W, right? Then we need to make this weight equals to W, because now there are two people, right? So there are basically two knapsack bags. Actually, you can actually transform the math from knapsack to the solution of the problem. So basically you have two knapsack bags, but your goal is not to add value, get the maximum possible value. Your goal is to minimize the weight distribution you give in these two knapsack bags, right? So when you have like dp of I, suppose you had the ith pair of books and you have current weight W. Suppose this is L and this is N, right? Suppose this is for L. You have the current weight W. Oh, where is going? Yeah, you have the current weight W. Then you need to make this weight equal to W. And there should be another thing, weight of N, right? So this gives us like a 3D thing, 3-dimensional dp W Nikhil. Because when I know that I am at the ith position, I am at the weight of Lavanya's bag is W, weight of Nikhil's bag is Wn, then the answer of the dp is nothing but the difference, right? So this dp can be a boolean dp, which say if it's 0 that means this is not possible, if it's 1 then this is possible, and the answer is nothing but given from the states, right? And so here you are checking if you can make W or not. because yeah. uh, the CS problem exactly like this. This is a classical problem. Oh no, this is not a classical problem. Actually, this is very similar to subset sum problem. So you should try subset sum on your own after you understand this solution for this one. We have to make a list of differences. Yeah, we need to make, and it can be positive values. Uh, and so we see that this is basically an n. This is n. What is the maximum weight this can have? It's nothing but n into the weight of each book. This is again n into 8 of each book. So the time complexity here becomes n cube, and each book's weight can be 300. So into 300 square, which is like too much, right? Like to solve all possible options. But so it's evident that you need to optimize this. But the how will you optimize? Like suppose you're stuck at the recurrence, which is like very basic, and you need to optimize it. Then you need to observe what things you can do in question. In question, you think nothing can more be observed, but what you observe in your solution is what are you using redundantly, or what are you not using it to its potential. Why is the DP array a boolean value, right? You are technically wasting one of the states. You can like convert a states into a value array for DP, right? Why do you keep it a state? So that's where we come to optimize, where we will not use DP as a boolean value to check if at the ith book can you make WL and WN, right? Instead of that, if you're at the ith book, uh, okay, we're still using it a boolean DP, but what we change here is that if you're at the ith element, then we remove a state of W. So we only have one state now. We combine the states into two. So why do you do this? Because what you are doing is for Lavanya, if you add that book in Lavanya, then this weight increases, right? Because all values in the difference area are positive because you have taken the absolute. So if you add it in Lavanyas, then this increases. But if you don't take in Lavanyas, then this increases, right? And you are taking the difference of this, right? Which is the answer. Then why do you keep a different state? So yeah, just you find the difference. Instead of that, you can combine this state into this. Because suppose we have some value which is W1, W3, right? This is Lavanyas. And for Nikhil's, it's W2, right? Then our answer will be from DP of I comma W1 plus W3 and W2, right? These will be the three states from which we can get answer, because we see that that's possible to make, and hence DP of I comma W1 plus W3 comma W2 will be true. But then we are taking the difference is nothing but W1 plus W3 minus W2, right? So what if you store this weight itself, like W1 plus W3 minus W2 in a transition, right? So if the Lavanya takes it, then you add the weight. If Nikhil takes it, then you subtract the weight, right? And you don't care who has bigger weight, who has smaller weight, whose weight is in positive, whose weight is in negative. You just care about this difference, right? And each value, if you have some difference D right now, then each value, let's say W4, can either go in the positive part of D, that is, it contributes plus as plus, or it goes to the negative part of D, that is, it contributes in minus, right? So this helps us give the transition of all the possible options, where DP of I comma W is nothing but DP of I minus 1, of course, comma W minus X. Let's say X is the difference, Xi, of course absolute value, comma, let's say, or let's say max, because we just want it's like 0 or 1 dp, dp of I minus 1, comma, w plus x of I, right? So why this recurrence is, what this recurrence says is that if either you take it in the plus component, that is this part, right, either you take it in minus component. And why are we absoluting the minus component? Because if I take it in the minus component and it goes negative, then of course the state can't be negative, but the final answer is the state, which is always positive, which is the absolute value. So basically we make all the negative values positive and all the positive values negative. It's the same, because we don't care if Lavanya is positive or Nikhil is positive. At the end we are getting a positive value. So this transition state is an answer, only is a possible answer only if this value is 1, which is a boolean value, right? And then you can have the base cases. You think of the base case as like, if you have there no books, then the answer is 0, and for all other things the answer is not 0. Like for no books but weight equals to 1, the answer is not 0. And then you just, for the final answer, you just loop dp of n minus 1 comma or possible w's, and you find the minimum possible w you can make. So once you find them, you go in increasing w, and once you find the w, you just take it. Like that's the answer. Do you all have any doubts? Equal to prefix sum till index I. Yeah, the plus thing, why do you care about plus? Like you need to subtract you need to find the difference, right? So why do you need plus? Yeah, to get rid of state true. Yeah, anyone has any doubts? Yeah, it turns 3D DP into 2D DP if you do some merging and stuff. Yeah, I don't understand the doubt, but yeah, we can either take like 3 to n and 5 to L, or vice versa. We have 2 to the power n ways to solve it, true, but that's what a DP does, right? If you just write a plain recurrence in this, then it will be 2 to the power n. But if you just memorize it, you just don't you just like don't recalculate everything, you just store it, then it's just or of n times n into 300, which is n square into 300, which is like quite fast. If you want, I can like show you the code. So this is the code. This is the recursive code. Let's see if we can understand from iterative to recursion. So pause is nothing but I, sum is nothing but the current weight. So these are our 2 index transitions, and dp and v, the value of paired book. So we find the difference over here, and if we have already calculated, if you just remove this sentence, then your answer changes to the power n, And if you just add this, then it's so fast. So this is exactly what memoization is. So this is our base case. And uh, 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 dp of post comma sum is this guy min of both takes, and first take is if you add it in the positive value, if you add it in the negative value, and you always have the absolute of it, right? That's it. And dpr is n into 300 comma n, and then you just recursion is like a forward recursion. Yeah. Now if no one has doubt, then we can go on to the last problem for today. This is a really good problem. Like, initially when I was also preparing, I really liked this problem. I don't know if it's 1900 or not. I just think it should be. To come up with DP states, you need to understand what are the factors that affect if you want to solve a problem, right? So if you are like solving like for the equal gifts, you knew that what things were there that would affect. If so, the thing is the difference array that would affect the amount of weight that you currently have for each of them is what matters. So it's like all the important things is what matters, and then you need to make them into states and answers. You need to adapt to that situation. So in the grid problem, you knew that you just need to understand what cell you are in, and then you can have the transitions. In the frog jump, you need to understand which position you are on, which matters. In knapsack, you understand that the weight also mattered, the value also mattered, which was stored in the dp values, the position mattered, right? So that's some things that matter when you want to solve a sub problem. We just think of it as a plain brute force recursion. You will understand what are the things that matter, and all those things need to like be taken care of in the dp. So probably I think you should be like very, you should be good with the basic brute force recursion, which is exactly just what the question says. Just write it in code, recursion or something. No memoization. You should, because that helps you understand how the problem is going, and then you can optimize it. Like memoization is one of the optimization, but inside memoization we saw how we reduced one of the states, right? So all these you can do once you have the basic recursion or the idea of it. That will help you understand what are the things that matter, what are the things you need, and that will help you in the states and the dp transitions. I hope that answered. Yeah. So let's start with this problem. This is pretty cool problem. You are given a 2 into n grid, right? And you have certain types of dominoes. One is 2 into 1 domino, one is 1 into 2 domino, and one is an L-shaped domino, which is 2 like this, right? And you need to place these dominoes on the grid such that you completely fill the grid, and you just ensure that uh, all the cells are covered, and you can rotate you can rotate this L domino in any way. So if you can see, this can be rotated the only possible other way. Okay, so this can be rotated this can be rotated like this, right? Oh, this can be rotated this, and this can be rotated this, right? These are the 4 possible rotations you can use, right? and you need to fill the grid. So what you see is that if you take, and you need to find the number of ways you can fill the grid. Of course you can fill the grid, like it's pretty trivial, but how can you fill the grid, right? So how can you differently arrange dominoes? It's not the number of dominoes we use. Suppose if we use this domino like 2 into 1, suppose you have a 2 into 2 grid. Let me take a new example. uh, uh, Suppose you have a 2 into 2 grid, right? So you can take two vertical dominoes, fill it, right? Or you can take two horizontal dominoes and fill it like horizontal. You cannot take L-shaped domino because one cell will be missing then. If you take this L, then what about this cell, right? So you can't take, but number of ways is you take two horizontal, two vertical, it's two. If you add one more column, then here you can take two L shapes, right? Either this and this, right? So either you can take like this and this, or you can take like this and this. These are the two possible options of making L shape complete, right? And the second way is you can take one vertical, two horizontals, or three verticals, or two horizontals and then a vertical. All these are different combinations, because here vertical is ahead, here vertical is behind, and you need to find the number of combinations, and you need to give it modulo 10 to the power 4 or 5. This answer can be very large. So let's think. Okay, dp of I is dp of n is n minus 1 plus n minus 2 plus 2 into extra n minus 2, but extra n is extra n minus 1 plus dp of n minus 2. dp of I is the number of ways to fill n minus n cells, with cells first cell being filled and second cell empty. Number of cells in first cell yeah, iota, you have like a pretty good good like understanding of the states. Probably if you just make proper transitions, then that should work. 2 into extra n minus 2, extra n is extra n minus 1 plus dp of n minus 2. I don't know the counting problems. One. For Rudrojit, your solution is wrong. Yeah, your solution is wrong, but it's almost correct. This is just a small tweak that would be required. But yeah, so let's go on to the solution. So first thing is that you are given 2 into n. So they are like, when you are at the ith position, what are the possible ways you can make the grid? Suppose you have 2 into I columns, right? So one way is just take the horizontal domino, and in that case it's nothing but you have I minus 1 columns, right? And just answer for that and this. So if you just find this recurrence, then this is dp of I is nothing but dp of I minus 1, right? Second possible option is you take two horizontal dominoes, because of course if you take one horizontal domino, there's no other way to fill this thing, right, apart from another horizontal domino. So you take another two horizontal dominoes, and then you have I minus 2 columns. Oh, why is it moves? Then alright, technology is bad. Now you have I minus 2 columns, right? So if you just add this in a recurrence, then uh, plus dp of I minus 2, right? Now comes the L, which is the crucial part. So for L, you have a grid, and if you take an L, then what can you do? The first option is take an inverse of that L and dp of I minus 3, right? Second option is you take an horizontal this, right? So it's nothing but one cell remaining. This is another thing. You take an horizontal cell, now you have one cell remaining, but in row I minus 2. Initially it was in row I minus 1, right? The third thing is you have, yeah, you can't take a horizontal vertical here because this cell is not empty. So you either take horizontal, and now you do the same thing. Either you take an L inverse and then answer is this, right? Or you just you take another horizontal and answer is the same thing. You go for one cell empty and over here, right? And this you can just multiply it by 2 because this is nothing but if you one way is taking this L, the other way is taking this L, right? It's this L and this L, both have one cell remaining over here. And uh, so there are two ways. One way is what iota suggested, which is also possible, and one way is which Rudrojit suggested. And my solution was the one which was very similar to what Rudrojit suggested. So in my solution, I calculate another thing, which is, let's say, dp1, right? So this is nothing but this, and let's say I have dp1 especially for L cases. So what exactly does my dp1 say? So dp is when I know that both cells are empty or both cells are full, right? dp1 says that if I'm at the ith position, then I have a grid and I have one cell empty and one cell full. Or I have another extra cell, whichever you can just do, it's I or I minus 1. And you need to find the answer when I have one cell like this. So if I have one cell empty, then either I can take an horizontal, it's nothing but dp1 of this cell where I have one cell empty but it's I minus 1, or I take another L, right, which is dp of I minus 2, right? Because now I have both cells empty. So my dp of 1 says that I have only one cell empty in the ith column, and my dp of I says I have both cells empty in the ith column. So in the dp1 recurrence, dp1 position I is nothing but dp1 position I minus 1, because I take an horizontal and now I have one cell remaining in I minus 1th column, right? I don't know, I don't care which, if it's an upper cell or a lower cell, right? And what is the second option is I take an L, which gives me an answer plus dp of I minus 2, not dp1, right? And this is basically, here we need to add the L case, where suppose I take an L. So L gives me that two options to take L, right? And for each L I take, it's nothing but dp1 position I minus 1, because one cell is remaining. If I take an L, then one cell is remaining in the I minus 1 column, right? Yeah. So this is the thing. This is the final recurrence for both the DPs. Yeah, DP of I comma 0, I comma 1 will be equal. That's why we don't care and take like a 2 into thing. Uh, but that's actually a very good way to think. Like, you just separate all possible cases, and even if it's different, it's very easy to transition between states. It's not difficult, right? If you have a clarity of what the states are and how the states are working, then it's for your benefit to work. So yeah, this is the final recurrence. This is the code. So dp and t is nothing but dp1, and the base cases are, if they are 0 2 into 0, then it's one way to make 2 into 0 cell, which is don't take anything. And if it's 2 into 1, then we have a vertical domino only. And yeah, if there's 0 rows, zero columns, but there's one cell empty, it's not possible to have one cell full and one cell empty, right? So this is 0. And if there's one cell empty, then you just take one L. So this is 1. Okay, here I have taken, like, in the explanation, I know how do I annotate. Yeah, in the explanation I told that we have a grid of annotate. Yeah, we have a grid of 2. Oh, so in explanation I told that we have, like, for the column I have one cell full and one cell empty. In this solution I have both cells empty, and in the next column I have like one cell full and one cell empty. That's why this is like I minus 2 into transitions. It should be I minus 1 if it's like, depending on how you think. That's why the base case is slightly different. This is possible because this is nothing but a matrix. It's like a 2 into 2 matrix where you have these both are full empty and this is full, so this is an empty possible option. That's why this is 1. And dp of I is I minus 1 plus I minus 2, and the both 2 times nothing but the dp1, and dp1 is nothing but dp of I minus 1 plus t of I minus 1. For this case, for my case, it was dp of I minus 2, because again the minus 1 problem, right? So it totally depends on how exactly you think. That's why it should be like, you should be clear on what your states exactly mean. Yeah, and you need to take modulo. That's why I have like different functions to add using modulo, and you just print it, right? That's it for today. Do you have any doubts? Would this problem be expert rating on CF? I don't know. Initially I found it hard, so I just gave it a 1900 rating. But all problems are easy when you know the solution. So I don't know. Probably Avigna would better judge this problem. Its rating.